Well, continuing on from the last class, um, we were talking about the difference between the isotropic phase, which looks something like this, where the molecules represented by red arrows are pointing in all different random directions in space, versus the nematic phase, like this, where the molecules tend to be aligned up or down along some axis. Okay? And so the next step is to define an order parameter that can characterize the nematic phase. Right? So we want some kind of mathematical object that represents what's the magnitude and direction of the nematic order. So we were in the midst of constructing such an object last time. And so the idea was that we were going to define the orientation of each molecule as a unit vector. So there's some unit vector L hat, and that would be for molecule number I. Okay? And then we could say, let's try to average all those orientations. It sounded like maybe it would be a good idea, but it's not. Okay, so that is what made the polar order parameter the vector m could be defined as the average of all of the L's. That is as take all the L's and add them up and divide by the number of molecules, like that. That makes a vector. That's a nice, well-defined object. The trouble is it's zero in the nematic phase because half the molecules are pointing up and half the molecules are pointing down along that axis. So that is not going to work as an order parameter for the nematic phase. So we have to try something else. Okay? So now I'm suggesting let's try the outer product of an L with an L. All right, so we could define a tensor order parameter T as the average of L tensor product with itself. Or for people who like the dyad notation, you could just say L, L, like that. Okay, that looks like another good thing to try, right? So this is writing it in an abstract tensor notation. We could also write it in component notation as T component alpha beta is the average of L alpha L beta, like that, where alpha is X, Y, or Z, and beta is X, Y, or Z. Okay, so now I want to test out whether this looks like it's suitable to be a nematic order parameter. So I want to figure out what this is in the isotropic phase and what this is in the nematic phase and see if those things are different from each other. Okay, so let's do it. In the isotropic phase, well, let's figure out these components. Right? Well, for one thing, let's look at the diagonal components. Right? So components like T sub XX, and that is going to be the average of LX times LX, right? The average of Lx squared. Well, this is an average of something which is always 0 or positive, right? So it must be 0 or positive. Okay. Likewise, we have Tyy is the average of Ly squared, and Tzz is the average of Lz squared. Right? Well, so what can we say about these numbers, right? Well, for one thing, we know that L is a unit vector, right? And so the magnitude of L, that is Lx squared plus Ly squared plus Lz squared, right? And that has to be equal to 1. That's what we mean by a unit vector. Okay. What else do we know, right? Well, we know that the isotropic phase is isotropic. That is, all directions are the same. So because all directions are the same on a statistical average, we must have that the average of Lx squared is equal to the average of Ly squared and equal to the average of Lz squared. If they weren't equal, then the phase wouldn't be isotropic. So we have three numbers which are all equal to each other and they have to add up to 1. So the numbers must be 1/3, each of them. Okay, so that's part of the tensor. All right. Now, what about the off-diagonal terms like Lx, Ly, for example? Right. Well, we know that in the isotropic phase, there are molecules with the Y component positive, and X could be positive or X could be negative, right? There's a symmetry between those two things. There's no preference to go one way or the other. So this will have to average to 0. Right? It is equally likely to be positive or negative. And similarly for all the off-diagonal terms. So the tensor in the isotropic phase has to be 1/3 in each of the diagonal positions and 0 in all the off-diagonal positions. So this is the tensor T alpha beta in the isotropic phase. Okay, now let's compare it with the nematic phase. Okay, and to be specific, I have to say which way the nematic phase is aligned. So let's say in the nematic phase, aligned along the Z direction. And let's suppose there is, at least for the moment, let's suppose there is perfect nematic order. That is, all the molecules are perfectly aligned along the Z direction. So half of them are pointing in the plus Z direction, half of them are pointing in the minus Z direction. Okay? So all of the L's are plus or minus Z hat. Now let's figure out the components of this T tensor. Well, T, Z, Z. Okay, so that's the L, Z times L, Z averaged. Okay, so this is the average of plus or minus 1 squared. So it's the average of 1, right? This is just 1. What about TXX? Right, well, that's the average of LX times LX. But L is always in the Z direction, plus or minus, right? So LX is 0. It's the average of 0. So that's just 0. Right? Similarly, TYY is 0. What about any of the off-diagonal things, like TXZ, right? That's the product of 0 times plus or minus 1. Oh, well, that's 0 also, right? Everything is 0 except for TZZ. So the tensor is T alpha beta. That is 0, 0, 0, 0, 0, 0, 0, 0, 1. Right? In the case of perfect nematic order along Z. Okay, well, so this is good news, right? We're making progress. We are making progress because this tensor is different depending on which phase we're in. Now, considering that T has these two possible forms, okay, I could make a couple of cosmetic changes just to make it look nicer. Okay? So one thing that would make it look nicer would be, wouldn't it be nice if we had a tensor that's 0 in the isotropic phase, because there's 0 nematic order in the isotropic phase, and it's non-zero in the nematic phase, right? Well, I can do that, right? I can do it by just subtracting off what is the tensor in the isotropic phase. So for that beautification step, let's say we will define a new tensor, T prime alpha beta, to be T alpha beta minus what the tensor is in the isotropic phase, which is this 1/3, 1/3, 1/3 on the diagonal. I could write that nice and compactly with the Kronecker delta. It's 1/3 of delta alpha beta, because this delta alpha beta is the identity tensor, right, with the components 1, 1, 1 along the diagonal. Okay, in that case, this tensor T prime is going to be 0, 0, 0, 0, 0, 0, 0, 0, 0, right, in the isotropic phase. And T prime alpha beta is going to be this thing minus 1/3, 1/3, 1/3 in the nematic phase, perfectly aligned along Z. Okay? So if I subtract that, that makes minus 1/3 minus a third, 2/3 along the diagonal, and 0 in all the off diagonal places. All right, so this is if there is perfect nematic order along Z. This looks pretty good, right? I could totally stop here if I wanted to. However, there is one further step that people normally make to make things look nicer, okay? And that step is, this T prime, it has these factors of 1/3 and 2/3 in it. It doesn't look like it's perfect order. It looks like it's sort of 2/3 order. So if we want it to look more perfect, let's just multiply everything by 3/2. Why not? Okay, so let's define a new tensor. Okay, so we'll define a tensor Q alpha beta to be 3/2 times this T prime alpha beta. Or we could say that is 3/2 times T alpha beta minus 1/3 delta alpha beta. Or we could say that is 3/2 times the average of this L alpha, L beta, right? That's my definition of T, minus 1/2 delta alpha beta. Or if we want to put everything into one set of averaging brackets, we don't have to, but we can. We could say it's the average of this 3/2 L alpha L beta minus 1/2 delta alpha beta, like that. Okay, so this is the standard definition of the nematic order tensor. So I will put a box around it. Ah, so beautiful. Okay, that is then gets a box around it. And this is a tensor order parameter for the nematic phase. And so we know what this is for a couple of examples. Right? We already know for one example in the isotropic phase that the Q alpha beta tensor is 0, because that's the way we constructed it. It has to be 0. We know that in the nematic phase with perfect order along Z, that we have the tensor is 3/2 times what was down here. Okay? So it's minus a half in those positions, and 1 in that position. Whoops, wrong pen. Minus a half, and 1. With 0 in the off diagonal places. Okay, now what can we say? Okay. Let's consider a few other cases. What about the case of a nematic phase with partial order along Z. So by partial order, I mean the molecules are mostly aligned along the plus or minus Z axis, like my pencil, right? But not perfectly. There's a range of orientations back and forth. Okay, so for each of the unit vectors, we could write it in spherical coordinates as L is sine theta cosine phi, and sine theta sine phi, and cosine theta, like that, right? Where theta is the angle down from the z-axis. I say this is z, x, y. Theta is the angle down from the z-axis, and phi is the orientation in the xy plane. Okay, let's figure out what is the Q tensor in this phase, okay, with the partial nematic order along the z direction. Okay? So we have different components to figure out. Okay, so let's start with what is QZZ. So this is the average of 3/2 LZ LZ minus 1/2 delta Z Z. All right. So this is the average of 3/2 LZ squared, right? Well, LZ is the cosine of theta. So it's 3/2 cosine squared theta minus 1/2 delta ZZ. Well, delta ZZ is 1, okay? So it's just the average of 3/2 cosine squared theta minus 1/2. It turns out that this object inside the brackets is a standard thing in mathematical physics. And it is labeled as P2 of cosine theta. And the word for that is the second Legendre polynomial. In cosine theta. Okay. This is something which might possibly be familiar to some of you from courses in electromagnetism or in quantum mechanics, okay? Because it comes up in those branches of physics also. Okay, so QZZ is this thing, which is the average of P2 of cosine theta. And in liquid crystal science, this quantity, the average of P2 of cosine theta, is given the label S. And it is called the scalar order parameter for reasons that I will go into in a few minutes. Okay, so QZZ is this thing S, right, which comes from the average of P2 of cosine theta. Okay, what about the other quantities, like for example, QXX. All right, let's figure that one out. Right? So QXX is the average of 3/2 LX minus a half delta XX. Right? So that's the average of 3/2. LX is sine theta cosine phi. So that is squared, sine squared theta cosine squared phi, minus 1/2 delta XX is 1. Okay, so what is this? Right. Well, we have a phase that has partial order in the z direction. That is to say that it's not ordered in any particular direction in the xy plane. Okay? The molecules are randomly distributed anywhere in the xy plane. Okay? That means that the angle phi could be pointing anywhere in the xy plane. In that case, so we'll say phi is randomly distributed, or a better word would be uniformly distributed in the xy plane. Oops. So from 0 to 2 pi. In that case, the average of cosine squared phi and the average of sine squared phi are both equal to a half. So that means that QXX is going to be the average of 3/4 sine squared theta minus a half. Now let's use the trig identity that sine squared theta is 1 minus cosine squared theta. So it's minus a half. So this comes out to be the average of 1/4 minus 3/4 cosine squared theta. This is just negative a half times the average of 3/2 cosine squared theta minus a half. That's the same thing that we had before, right? So it's negative a half of S. Is this all right for you guys? I'm seeing some hesitation around the room. Okay, no, you're good with this? Fair enough. All right. By the same argument, QYY is also minus a half S. It all just repeats the same way. And it makes sense that QXX and QYY should be equal to each other because there's nothing special about X or Y, only Z is the special direction in our set of assumptions here for the nematic phase. What about the off-diagonal elements? Okay. What about, for example, QXZ. Right? So that's the average of 3/2 LX LZ minus 1/2 delta XZ. Well, delta XZ, that's 0. Okay. What about the average of LX times LZ? Right? Well, if LZ could be positive or negative, and LX could be positive or negative, and it's not correlated with LZ in any way. So this thing is going to average to 0. By the way, I shouldn't have put those brackets here. That's better. So QXZ is 0. The same, by the same argument, QYZ. And for something like QXY, the average of LX, LY minus 1/2 delta XY. That the delta XY is 0. And likewise, LX and LY are equally likely to be positive or negative. And so this all will average to 0. So this tells us then what is the Q tensor for this case of partial order. Right? That the Q tensor alpha beta is going to be a tensor which is minus 1/2 S, minus 1/2 S, S on the diagonal, and 0 in all the off diagonal places. Or if we factor out the S, it's just S times minus 1/2, minus 1/2, 1, 0, 0, 0, 0, 0, 0. Okay, so this is the case of a nematic phase with partial order along Z. Okay. What about if we have order in a different direction? For example, a nematic phase with partial order along X hat. That could happen for sure, right? We could have our molecules aligned mostly this way. So there must be a Q tensor to describe that, right? Well, we can figure that one out by analogy with what we just did, right? So here, what we just did here was to find the Q tensor with order along Z, and we can see that Z is like a special direction in the tensor, right? The ZZ position is where you get a 1. The other two positions that are not so special, they get minus 1/2. Right? So similarly, we would say if the partial order is along X, then the Q tensor must be S times a tensor that's 1 in the XX position and minus 1/2 in the other diagonal positions and 0 off of the diagonal. Good so far? Right. What about if it's partial order along Y? Anybody want to take a guess? I think you're guessing, right, that the special position will be the YY position, right in the middle, right there. Okay, and so if it is 5 partial order along Y, then we would have our Q tensor. That's this scalar S, and then minus a half, 1, minus a half, 0, 0, 0, 0, 0, 0. Okay, now here's a trickier question. What if it has partial order in any old diagonal direction? Okay, that's not the X direction or the Y direction or the Z direction. Let's say there's partial order along a different unit vector. Let's call it n hat, where n hat is any vector. Let's say it's diagonal, for example. Okay, but it has components along X or Y or Z. How are we going to figure that one out? Right? Well, we can still work by analogy with what we did before. Okay, so let's go back to what we have for partial order along the Y direction. Okay, so if we go back to this thing with partial order along the Y direction, I can rewrite that in a clever way. Okay, let me do a little bit of clever rewriting. I want to say it is S times the difference of two tensors. Okay, so let's write it as, well, something minus something. Okay, I want to say the thing that I'm subtracting off is a half, a half, a half along the diagonal. Okay, and so what goes here must be 0, 0, 0, 0, 3 halves, 0, 0, 0, 0. Okay. This thing for sure is 1/2 of the identity tensor, alpha beta, delta alpha beta. What about the first of these tensors that I wrote here? Well, this is 3 halves times, well, 0, 0, 0, 0, 1, 0, 0, 0, 0, like that. Okay. So this is a tensor which has only a 1 in the YY position. Okay. We could write it as this tensor as y hat sub alpha, y hat sub beta, right? Where y hat is the vector 0, 1, 0. Okay. So this tensor, you know, the y hat alpha, right, means the alpha component of this vector. Okay. So it is 0 if alpha is, this is 0 if alpha is X or Z, and it's 1 if alpha is Y. The same thing for beta in the second factor. Okay, so if I multiply those two things, then I get that I get a tensor which is 0 unless alpha and beta are both equal to Y. Okay, so that is this tensor right there. And then I multiply it by 3 halves. So putting those things together, I would say for partial order along y, that Q alpha beta is equal to S times 3/2 y hat alpha y hat beta minus 1/2 delta alpha beta. Now, that inspires us to work by analogy. We can say, what if we have partial order along any unit vector n? In that case, Q alpha beta must be this scalar S times 3/2 n alpha n beta minus 1/2 delta alpha beta. So this then becomes our expression for the order tensor of a nematic phase with partial nematic order, not perfect, but partial, some order, which could be oriented in any direction, a direction n hat, which might or might not be one of the 3 x, y, z coordinate directions. It might be some diagonal direction. It could be anything. So this is an important expression about how to describe the order of a nematic phase. Right? And we, about how to describe the order of a nematic phase. Let me mention a couple of things about this expression, which are not so mathematical, but sort of general bits of physical interpretation. Right? One kind of physical interpretation is that we can notice that the Q tensor is a product of these two things. Okay. The first factor up in front describes the magnitude of nematic order. So this is, the S is the average of P2 of cosine theta, where theta is the angle between the molecule, the molecular axis, L, and N, right? So theta, when I introduced it to you before, theta was the angle between the molecular axis and the z-axis. That was true when the phase was oriented along z. If the phase is oriented along n, then it's the angle between the molecular axis and n. There's nothing special anymore about z, it's just n is the special thing. So this S, the factor in front, is information about the magnitude of nematic order. The second factor is information about the direction of nematic order. The direction is encoded into this tensor. So it's encoded in a slightly complicated way, but it's not that complicated. It's encoded, through a vector n which gets multiplied with itself, and you multiply by 3/2 and subtract off half the identity matrix. So here we have a combination of information about the magnitude of nematic order and information about the direction of nematic order. Now let me compare that with something that we had way back at the beginning of the semester with the Ising model. When we were dealing with the Ising model, we had an order parameter m, right? And this was just a number on a scale from -1 to 1. We could, if we wanted, separate this to be an absolute magnitude of m times a sign, which is ±1. And in this case, this absolute magnitude, this is the magnitude of Ising order, and the ±1, this is information about the direction of Ising order. It's a very simple direction because there's only two possibilities, right? Either up or down, right? But it's, you know, a factor describing magnitude times a factor describing direction, okay? The same way as for this tensor order parameter for the nematic, right? That it's a factor describing magnitude times a factor describing direction. And that kind of guides us to saying, you know, we should, these are the two things that we should think about when we think about a nematic phase, right? We can think about what's the magnitude of the nematic order, that is, how well aligned are the molecules along some axis versus the direction of the nematic order, which is, you know, which axis are they aligned along? And these are two big issues in the study of liquid crystals, right? And so, you know, more or less, I would estimate that information about the magnitude is something like 10% of liquid crystal science. And information about the direction of order is something like 90% of liquid crystal science. But they're both important, right? And so these are, you know, both things that you need to think about. Let me say a couple other things just briefly about both the magnitude and the direction. Okay. So for the magnitude, that's this S, that is P2 of cosine theta on an average. That is 3/2 cosine squared theta minus a half on average. We might say, you know, what's the range of possibilities that this S can be? Okay. So we know in the Ising case back here, right, this magnitude is on a scale of 0 to 1, right? That is 0 is disordered, 1 is perfectly ordered. Okay. So here for this nematic problem, we have S equals 1 in the case of perfect nematic order. That is, if theta is always 0, the cosine of theta is always 1, then you have 3/2 times 1 minus 1/2. So it's 1. We have S equals 0 for the case of no nematic order. That is in the isotropic phase. In between, that is for S between 0 and 1, that is some partial nematic order. And that's the normal situation in any experiment that's done at, non-zero temperature, not 0 Kelvin. Now, there's also a weird feature of this expression, which is that, suppose theta is always 90 degrees. That is, suppose that the molecules, are randomly distributed anywhere except in the z direction, or except in the n direction, but randomly distributed in a plane. Okay? If theta is always 90 degrees, then the cosine of theta is always 0. And then we could weirdly say S equals minus 1/2. Right? That is an odd situation, which is a mathematical possibility, but it doesn't come up physically very often. And that is some negative nematic order. So that is like saying that there isn't a direction where the molecules are aligned. There's a direction that the molecules are repelled from. And so they tend to avoid the z direction and accumulate anywhere in the xy plane. So that would still make z a special direction, but it would be a special direction that the molecules avoid. And then the range of minus 1/2 up to 0, this is like partial negative nematic order. So it's a mathematical possibility, but it doesn't happen very often. Normally, we will have this situation where there's partial nematic order, or S equals 0. There is no nematic order. Let me say another thing about the direction, and then I have to stop for now. Okay, let's see. So for the direction, the direction is it's represented by a tensor, which is this 3/2 n alpha n beta minus 1/2 delta alpha beta. This is a tensor, and the tensor carries the information that there is order along plus or minus n-hat. Okay. Typically, people want to describe that in a quick way because we want to say quickly what's the orientation of our sample. Okay, so if we have a bunch of molecules pointing, in a distribution of orientations like this, we want to quickly represent it. And it's kind of a pain to talk about this whole tensor. wouldn't it be nice if we could just talk about n by itself? That would be easier for us, right? So we often do that, okay? And we often do that, and when we do that, we say n is the director of the nematic phase. So in a picture like this one, we would say, okay, here is a vector n, which is along the axis, the favorable axis for nematic order. Of course, we could equally well draw the negative vector. Those two things represent the same ordering, the same physical state. Those two things give the same tensor right there. Sometimes you will hear people say a statement like n is the average direction of molecules. When you hear people make a statement like that, you can say, well, that's kind of true in a loose way, but it's not rigorously mathematically true. Okay, it's not mathematically true because we already talked about averaging the molecular directions. It doesn't work, right? What people really mean is that n is one of these two black arrows. One of these two arrows, okay, that goes along with this tensor. Right? That's what they mean, even if they don't know that's what they mean, right? Because nematic order is this kind of tensorial order. It's not a vector order. And the vector is just a shorthand way for describing things. Okay, I'm over time because I get so passionate about this particular subject. So I'm going to stop talking for now. I will be glad to answer any questions about this. And then one student also had a question about some of the tensor manipulations, like on the homework, but an example from a past exam. So if you want to hear about that also, please stick around. Okay, sorry for going over time. I'll see you guys on Wednesday.
Will the answers to the questions be in your recording?
If you want them to be, sure.
Yeah, just because I have to go to TA. So
no problem. Go TA.
Excuse me. Do we have class on Wednesday?
Oh, wait. What an excellent question. The answer is no. We do not have a class on Wednesday because Wednesday is a US holiday and a Kent State holiday. So we do not have class on Wednesday. So I will see you guys on Friday, not Wednesday. Okay, I better send out an announcement to the people who have already left. Yes, thank you. Good point. Okay. Questions about the nematic first, and then I'll do the questions about the tensor manipulations. Okay. Anything about the nematic? No. Let's move on then to the tensor manipulation. Okay. So, Johan, right? So you were looking at one of the old tests that I posted, and there was a question which was something like simplify an absolute value, right? So if you have u and v are two vectors, let's simplify u cross v magnitude squared. right? Is that the question, Johan? Okay. Sure. Let's talk about how to do this. So let's, if we have any vector W, okay, so let's just say W is this U cross V. And we want to simplify W magnitude squared. Okay. So we know that the magnitude squared means the vector dot itself, right? W dot W. Okay. And we know that we can write a dot product in tensor notation, right? As WI, WI, where we are automatically contracting over the index I. Okay, so now let's just keep working. So we need to know what is WI, right? Well, W is related to U and V, right? And so we have the relation that WI is epsilon ijk uj vk. Okay. So we could write this. Let me substitute this in for the first WI factor. Okay. Whoops. So W, whoops, that's not what I meant. This, it equals epsilon ijk uj vk. Now, I want to write another copy of it. Okay. So I substituted in for the first one. Now I want to substitute in for the second one. Okay. So maybe I might guess. I'm going to show you a wrong thing first, and then I'll show you the right thing. Okay. Here's a wrong thing. I'm going to write epsilon ijk uj vk again. This is a wrong thing, okay? It is wrong because now look, I have 4 j's in this expression and 4 k's in this expression. That's bad, right? It creates expressions that don't make any sense. Right? So I'm not going to do that. Let me erase that. Instead, I can just write the same thing again with different dummy indices. Okay? So I could say WI is that, but it's also epsilon I L M U L V M. Okay? Because this thing and this thing mean the same thing, right? This thing and this thing both mean I'm adding up over, well, this index is X, Y, or Z, and this index is X, Y, and Z. Okay? And it doesn't matter whether I call the index in this position J or L. And it doesn't matter whether I call it K or M, right? Either way, I get the same thing here. Okay? It's the same as if I were writing software and I want to write a loop to say I'm going to add up, all the numbers, from 1 to 10 squared, right? And so I could say, let I equal 1 to 10 add up I squared. I could say, let j equal 1 to 10 add up j squared. It doesn't matter what I call the variable. I get the same answer. So now in my expression for wi, I will not reuse the j and k indices. I will say epsilon I lm ul vm. So this is an expression which is summed over j. There's two j's. And it's summed over k, because there's two k's. And it's summed over L, because there's two L's. And it's summed over M, because there's two M's. And it's summed over I, because there are two I's. Okay. So this is a perfect expression following all these tensor rules. Now, I can keep simplifying by rearranging the factors. Right? So I will put the epsilons together, I, j, k, epsilon, I, L, M, U, J, V, K, U, L, V, M. I can rearrange the factors as long as I keep the same indices on the same objects. Now, I can use the identity that we talked about. Right? Remember, we have an identity for what happens when you have the product of two of these epsilons, two Levi-Civita symbols. Right? And so we get first deltas where the second index matches the second index. So delta JL, delta KM minus what happens if the second matches the third, delta JM, and times delta KL. Okay, so this is now delta JL, delta KM, minus delta JM, delta KL, times UJVK, ULVM. All right. Now I'll distribute things, right? I'll put this factor times each of those two terms inside the parentheses. So here, maybe I better copy and paste that. Oops. What I meant to do. Okay, so W squared is equal to this thing. Okay, so that is equal to delta JL, delta KM, UJVK, ULVM, minus delta JM, delta KL, UJVK, ULVM. Now, I can keep simplifying because whenever we have a delta contracted with something, that makes our lives very easy, right? And so, for example, when we have a delta Km contracted with Vm, that makes a Vk. So there, I just did the sum over m. I'll do the sum over m in the second term. Delta jm vm, that makes a vj. Now let's do the sum over L. So here I have delta JL UL. That makes UJ. Here there's a delta KL UL. That makes UK. And then the remaining terms to write, the remaining factors are UJ VK here, minus, and here there's also UJVK. Okay, so now what? Now I'll rearrange the factors to put the pieces with the J index together. So this is UJ, UJ, VK, VK, minus UJ, VJ, UK, VK. Okay. Now UJ, we can recognize as U dot U, or equivalently, that is the magnitude of U squared. Similarly, VK is V dot V, which is the magnitude of V squared. VJ is U dot V. VK is also U dot V. So this whole thing simplifies to U squared V squared minus U dot V squared. Okay. So this is what we were trying to prove, right? That the magnitude of U cross V quantity squared is equal to U squared V squared minus U dot V quantity squared. Okay, so you know, this is what I was looking for on that old test. Now, Yuhan, you said in your email, right, you knew how to prove this with a different method, right? And probably what you were thinking of was a more geometrical method, right? That U cross V is a vector with a magnitude that is, you know, magnitude of U times the magnitude of V times the sine of the angle between them, right? Yes, right. And so for sure you could do that. And that would probably be fewer steps than going everything that I just went through. Okay. Even so, one nice thing about all the steps that I went through here is that you know, they're all sort of mechanical, right? The steps individually don't require a whole lot of creativity, right? That it's all sort of normal simplification. And it may be unfamiliar in the beginning, but it's a very standard sort of manipulation that you just get used to. And so then you can generalize this to complicated stuff with higher order tensors, and it all just kind of works step by step. And it seems like a lot of work when I'm showing everything for the first time, but once you get used to it, I promise it gets easier.